Okay, so welcome to graph theory. So this is the first week. So today we're going to give you some motivation. Okay? Why should you study graph theory if you're a computer science student? And we'll also cover or briefly overview the topics that we're going to discuss for this semester. And of course, the grading policy, the midterm finals. And so I think today we're going to start with some basic definitions, the most fundamental definition in graph theory, and some properties. That's for today, okay? All right, so since this is graph theory, so we have to start with graph, okay? So what is a graph? So, well, basically, a graph is like you have a bunch of circles, right? And you have some line segments connecting these different dots or different circles, okay? Like this. And then you have a graph, okay? So this is one graph. And you can also have a graph like this, okay? This is also one graph. All right. So I'll say the most important reason that we want to study graph for computer science is that we can use graph to model different kinds of systems. Right? So you can, for example, use graph to model a social network. So if you're considering a social network, then these dots, they can be users or user account. All right. And so if these circles are user accounts, then what will these links be? Can you think of any physical meaning for these line segments between user accounts? Friendship, right. Right. So that's for social network. And you can also consider like, say, computer networks, okay? Well, so since this is a computer network, then these dots, they are just devices. It can be your smartphone, your computer, your laptop, your, yeah, basically any device, okay? Computer, smartphone, right? And what would the physical meaning be for this link when we discuss computer networks? So this can be communication links, okay? Okay. So for example, this can be like a Wi-Fi AP or a satellite, okay, or a router, right? Okay. So any device that is capable of communicating with others, then this can be treated of as a device in this kind of computer networks, right? Then this, well, for these examples, these communications are like wireless communication. But for some like Ethernet, then the link or the communication will be wired. Okay. So all these different kinds of social networks, you can also consider like vehicle network, or you can consider like some networks formed by animals, okay, or molecular, all right? So really there are different kinds of very complex systems in computer science that can be modeled by graphs, okay? So the reason that we want to model them using graphs is because we can then study the structure of these complex systems, okay? So you can ask some simple questions like, is this network connected, okay? Is it prone to fail, okay? Suppose I attack one of these devices, will I then disconnect the whole system, okay? It's like the strength of the whole network, okay? Is it weak, okay? Is there a single point of failure, right? So, and also you can study like what is the best way to go from point A to point B, okay? And if you have this information stored in a graph, then usually there will be some efficient algorithm that can compute the desired goal, okay? So usually by modeling your problem as a graph, this is usually a very efficient first step, because the second step usually is just apply some graph algorithm, all right? So yeah, so in short, if we can model a complex system using graphs, then we can use some graph algorithms to solve your problem, okay? That's, I'll say, the most important reason for computer science students. All right, so, for this course, we'll focus on some properties of the graph, because, you know, if you want to design efficient graph algorithms, you have to first understand some basic properties about graphs. So we're going to study graph properties and some problems on graphs, and also some algorithms to solve this graph problem. Right. So let me give you the topics. It will be covered by this course. All right, so I think we'll spend like the first 3 weeks discuss some fundamental simple properties about graph. And after the first 3 weeks, the first, I'll say, serious graph problem that we're going to consider will be matching. All right, so what's a matching? Okay, so say this is your graph, okay? What I mean by a matching is just a set of edges, all right? Like this. So this is not just any set of edges, okay? So for a set of edges to be a matching, these edges, they cannot be, they cannot share endpoints, or they cannot touch each other. So you can see that these two green edges, they do not touch each other, right? So this makes them a matching. Right? And so for matching, there are different variants of problems that we can consider. For example, what is the largest matching you can find in a graph? By largest, I mean the most edges you can find without touching each other, right? So maximum matching. Okay, so we measure like the quality of maximum matching by counting the number of edges. Okay, but also you can assign weights, right, to these edges. Okay. For example, I can say that, okay, well, we have some numbers associated with these edges. Okay. So for example, these numbers can represent like the throughput when you consider Wi-Fi, okay, or wireless communication, this can be your bit rate, okay? Or if you consider auction, okay, you have bidder, you have seller, this can be the prices, okay? And you want to match this bidder and sellers. So in this scenario where edges have weights, you do not want just to have a large set of edges. You want to make sure that the edges that you choose, they have a large weights, large total weight, okay? So you're going to sum up all the weights over all the edges that you choose and see whether you can maximize it, okay? So this problem is called maximum weighted matching. Okay. And we'll also consider a different type of matching problems. This is called stable matching. Okay. So for stable matching, this is a complete different setting. So you can imagine that you are like a dating agent, okay? So you have some clients, some male clients, okay, some female clients, and you want to match them, all right? For example, like you have, say, Chris, David, Bob. So these are your male clients, all right? And then you also have some female clients like Alice, Jen, say Jamie, all right? So your job is to match your clients in a stable way, okay? So I won't define what a stable matching here, okay? But I can show you that to find a stable matching, you have some addition. You have to use some additional information, okay? So for this additional information, every client has to provide a list, a preference list. Say for Alice, Alice's favorite is say David. So this is Alice's favorite, followed by say Alice's second favorite is David. Bob. And Alice's least favorite, Chris. Okay, so this is Alice's preference list. So for this stable matching problem, you have the preference list for every client. You have to match them according to their preference lists in a stable manner. Right. Okay, so we're going to spend some time discussing this variance of matchings and of course the solution, okay, the algorithm. All right, and it turns out that to solve, at least for the first two problems, the maximum matching and maximum weighted matching, to solve these two problems, you have to solve a different problem, okay? So the problem is called vertex cover. Okay, so what is a vertex cover? Once again, you have a graph, all right, like this. And for vertex cover problem, your goal is to choose some vertices. So I haven't defined vertex. Basically, a vertex is just like a circle like this or a dot. Okay, in graph theory, the correct terminology for this circle is vertex. Okay, so this is vertex, and this is H. Sorry, I should first define these terms. Okay, so this link or these line segments in graph theory, we call them edges. Okay. So these are edges. Okay. So don't worry, I'll give you the formal definition of a graph later. Okay. So, but first I want to give you some text about the discussion that we're going to have for this whole semester. All right. So back to this vertex cover problem. So once again, you have a graph, and yeah, I just mentioned that for this problem you have to choose some vertices. Okay. Some vertices, and your mission is to cover, okay? To cover what? You have to cover all the edges, okay? These are the edges. You have to cover them. So what do I mean by cover, okay? So suppose I choose this vertex, okay? Then which edges can be covered by this vertex? Well, intuitively I'll say, well, these three, okay? Because they are somehow related to this vertex. And it turns out that it's that simple, okay? So if once you choose this vertex, then all these three edges, which are incident, so the formal terminology is called incident, okay? Or like they are connected, okay? But anyway, the correct term to use is incident. So these three edges, they are incident to this vertex. Therefore, these three vertices, these three edges can be covered by this vertex. All right. Okay, so, but we just cover three edges. But for the whole graph, there are like 7 edges. So your mission is to cover all the edges in the graph, okay? So it seems weird because the original problem that we want to discuss is matching, and matching considers edges, okay? You want to pick the most edges you can without touching them, okay? So it's kind of, these edges, they are separate or they are independent, okay? It turns out that to solve this problem, you have to consider this seemingly different, there's no relationship between these two problems, okay? So we're going to consider this problem, and also we will reveal the connection between this vertex cover problem and the matching problem. So the secret relationship between these two problems is called primordial transformation. Okay. So this transformation can be applied to not just graph theory, okay? So whenever you have an optimization problem, say, I'm not sure if you have heard like linear program, okay, or mixed integer linear program. Anyway, you have some constraints, you have some objective function that you want to maximize or you want to minimize, then you have an optimization problem. So whenever you have an optimization problem, there's this magic transformation that can transform the original problem into a completely different problem. And hopefully this completely different problem can help you solve the original problem. Okay? It turns out that it's very often the case that we can use this transformation to solve the original problem. Okay? All right, so this is a very powerful, very general technique, not just applied to graph theory, but anyway, we're going to cover this transformation in this course, and we're going to see more examples about this transformation, okay? More specifically, we're going to discuss independent set. Okay, so we're going to apply this transformation to independent set and see what comes out. Okay. And by the way, this vertex cover problem is NP hard, meaning until today we have no idea solving this problem in polynomial time. Okay, yeah. So the best we can do is like to approximate the solution. Okay, to approximate the best solution. Or another way to put this is that if a problem is NP-hard, then the best algorithm that we can find the optimal solution takes exponential time, okay? So not polynomial time, exponential time, okay? All right, and then we'll consider another NP-hard problem called Hamiltonian cycle. This is another NP-hard problem. So let me first give you the definition or just an example. Okay. No. Okay, so this is a graph. Then the Hamiltonian cycle problem wants to find a cycle. Okay, well, a cycle is just like this. Okay, so you start from one vertex and followed by an edge, another vertex, and so on, and then you go back to where you start. Okay, that's a cycle. Okay. All right. So for this problem, you have to find a cycle. Okay, not just any cycle. You want to find a cycle that contains all the vertices in a graph. Okay. Like this. Okay. So this is a cycle, and it covers or it contains all the vertices in a graph. Okay, so this is a Hamiltonian cycle. Okay. Can we always find a Hamiltonian cycle in any graph? So given any graph, can you guarantee that there must be a cycle that contains all the vertices? No. Right? Otherwise, this won't be an NP-hard problem. Okay, so the reason that this is NP-hard is because it's it's difficult to tell whether there's a Hamiltonian cycle or not. Okay. So since this is an NP-hard problem, what we're going to discuss for this Hamiltonian cycle problem is to find some sufficient condition. That is, if I tell you that this graph has some certain property, then I can always guarantee that there must be a Hamiltonian cycle in a graph. Okay, that's called sufficient condition. Okay, once you have this sufficient condition, you can always find a Hamiltonian cycle. All right. So we're going to discuss some sufficient condition. Okay, and even though I phrase this as a sufficient condition, it seems like this is just some mathematical statement. But it turns out that to find this sufficient condition, we actually designed an algorithm. Okay, we've designed an algorithm to find a Hamiltonian cycle. Okay, and this algorithm can always find Hamiltonian cycle under certain conditions. Okay, and so those conditions are the sufficient condition. Okay, so we will also consider some algorithms. Okay. Okay. And I think the final topic that we're going to consider for this course will be connectivity. Okay. Basically, connectivity is a number. Okay, it's a number. So what this number indicates is that what is the minimum number of vertices that you have to remove in order to disconnect the graph. Okay. So for example, if you want to break or to separate or to disconnect the graph or to make it a disconnected graph, then what is the minimum number, what is the least number of vertices that you have to remove to achieve your goal? So for example, if you only remove one vertex, say this one, and by removing a vertex, you also remove the incident edges. So if this is gone, then these 3 edges are gone. Okay. But you can see that after I remove this vertex and the 3 edges, the graph is kind of it's still connected. Okay. You do not separate the whole graph. Okay. So it turns out that for this graph, you cannot separate this graph by removing just one vertex, okay? So, but you can do this by removing 2, okay? For example, if you remove these 2 vertices in the middle, right, then you get 1 edge here and 1 edge here, and they are separated, okay? So for this graph, the connectivity is 2, okay? And for this graph, the connectivity is, so what's the number of vertices that you have to remove in order to disconnect the graph? Just 1, okay? You can remove any vertex as long as it's not a leaf node, okay? So any internal node suffices. All right, so we're going to consider some properties about graph connectivity, okay? All right, so I think these are the 5 main topics that will be covered for this semester. Are there any questions? 有问题吗？虽然说是英文授课，但如果大家要问问题，如果要用中文，我觉得也很 OK。所以当然，如果你要用英文，当然是更好。所以到目前为止，有不清楚的地方吗？不过坦白讲，如果你有不清楚的地方，应该也蛮合理的，因为我很多东西都没有很仔细的交代，是让大家了解一下我们会讨论什么样的问题，在这学期。Okay. All right. So for this course, we have 1 midterm exam, and This is scheduled on the 8th week, and this accounts for like 25%. And we have one final. Okay, so both exams are open book, okay? But you cannot access internet, right? So open book. No internet. And we have 2 assignments. Each accounts for 10%. Okay. And the purpose of these assignments is to help you prepare the exams. Okay. And starting from this semester, for your assignments, we only allow handwritten reports. Okay, so this means you cannot copy paste some words from either say GPT or Gemini. Okay, you have to write it down. And we have a group presentation. And this accounts for 20%. Okay. And because the number of students for this course is not fixed yet, so I'll announce more details about this group presentation, okay, after the student list is fixed. Yeah, so I don't know, there's another 10% for class participation. Okay. So for this part, this includes like Q&A or any kind of interaction between you and me. And sometimes I may like save the last 10 minutes and that you to practice some problems. So I bring some papers so you can, have some exercise or practice about the material that we just learned. Okay. All right, so this is the grading policy for this course. Any questions? Okay. All right, so now we can formally define what a graph is. Okay. And by the way, all the course will be recorded and will be uploaded to YouTube, okay? You can go to YouTube and search this channel, TWKU123, and you can find the course recording. So to form a graph, first you have to define like the circles or the vertex set, okay? So for example, if you have a social network, then you have to first define the user accounts, okay? Okay, so for this example, we can say that the vertex set is just Alice, Chris, Bob, Jen, and David. Okay, so this is your vertex set. Okay. And then you have the edge set. Okay, so what is an edge? An edge is just a pair of vertices. Okay, so for example, in the context of social networks, we can consider like friendship. Okay, so say Alice and Chris are friends, and Jen and David are friends, and Bob and David are also friends. Then we have three edges, okay? Alice, Chris. This is the first edge. And Jen, David. This is the second one. And Bob, David. Okay. And by the way, for a set, there's really no ordering, okay, among these elements. So, yeah, so I didn't say that this that comes first in a set, no, okay? This is just one element, and another edge, okay? So there's no ordering because we consider set, okay? Okay, but anyway, we have three edges for this edge set, okay? And usually we use this notation, okay, to denote a graph. So it's a pair of vertex set and edge set, and then you get a graph, okay? So I would say the original definition of a graph is really very abstract, okay? There's no graph drawing, okay? It's just sets, okay? Whenever you have set, and then you can define the relationship between the two elements in a set, then you get edges, okay? So elements and relationships. Whenever you have elements and relationships among elements, you get a graph, okay? Okay, so to make sure that we're on the same page, I have to introduce some terminologies, okay? Okay, so sorry, this is kind of boring, but it's a must, okay? So in this age, we have two endpoints. So A and B. Okay, so whenever I say endpoints, it must be that I'm considering some edge. Okay, and I'm referring to the left and right vertices associated with this edge. Okay, so these are endpoints, and we will say A is B's neighbors. Okay, I'll just highlight the keyword that I want to stress here. Okay, so endpoints neighbors, okay? And so similarly, B is A's neighbors. Sorry, no S. And A is adjacent to B, okay? And or we may say like A and B are adjacent, okay? So whenever we use this word adjacent, it must be that we consider two vertices, okay? But when we consider one vertex and one edge that are kind of connect to each other, we use a different word. We use incident, okay? So say, let's call this edge E, so we can say A is incident to E, okay? Or E is incident to A, or A and B, so yeah, just these two, okay? Okay. Okay, so endpoints, neighbors, adjacent, and incident. So these are keywords for this graph, for this course. Okay. And sometimes I may refer to these vertices as nodes. Okay, so just node. And I may call these edges links. So these nodes and vertex, they are interchangeably, okay? And similarly, link and edge, they are also interchangeably for this course, okay? Yeah, kind of boring, but we have to do this. Okay, so the first property about a graph. So what is a kinetic graph? Or say you are writing a computer program and given a graph, you want to test whether it is connected or not. How to tell a graph is connected or not? So for example, is this a kinetic graph? And so this is one graph, okay? And this is one graph, okay? So is it connected? Yes, intuitively yes. And how about this? No, okay. Now the real question is how to define this formally. So yeah, we visually, we can tell that there are like two parts separate in this graph. And for this one, there's no way to like separate this graph. So it seems like it's reasonable to assume that this is connected. But we need a formal definition. And I don't want you to like memorize this definition. I want you to be able to come up with this definition, because this definition, although it can be like a very formal description, but at the end of the day, this all contains some intuition. Okay, so I want you to come up with this definition, like in a reasonable sense. 所以要给你一个 graph， 所以有2种方法去思考，就我刚刚说，你可以去思考，比如说你要写程式，你要设计演算法，你要怎么判断说一个 graph 是不是 connected，OK？ 你可以从这个角度去思考说，那我要怎么去定义一个 graph 是不是 connected，OK？ I mean, when you write your thesis, you have to define lots of things, okay? So it's a good practice to see how you define a concept, in a correct way. So any idea?
You can choose a connect point, a random vertex, and check that if there exists a path to any other vertex.
Okay, that's a good start. Okay, so but you mentioned a random vertex, right? So, but it seems like for your definition, it involves some randomness. So there's some uncertainty in your definition, right? Because perhaps the vertex I choose is a good vertex, in the sense that according to your definition, this vertex can be like connected to every other vertex in a graph. But what if I choose like a bad vertex?
It's okay. We can choose anyone.
Right. So I'll say we usually reserve the word random for the context when we actually need probability. We actually flip a coin. That's when we use random, okay? But there's no randomness for this definition, okay? So yeah, I think what you propose is that if you can find a vertex such that this vertex can be connected to every other vertex in the graph, then the graph is connected. Am I right?
Yeah.
Make sense? Okay, so 所以刚才同学说的是，如果你可以找到一个点，他没有说是哪一个点，反正你只要可以找到一个点，那个点可以让你类似连到这个 graph 的其他的所有点，那我们就会说这个 graph 是 connected. Okay. I won't say this is the standard way of defining a kinetic graph, okay? But your definition is absolutely correct, okay? So I said the standard way to define a kinetic graph is that a graph is connected if for every 2 vertices in a graph, so these 2, so for every, okay? You have to consider all possible ways of choosing these 2 vertices, okay? It can be these 2, these 2, these 2, these 2. You have to consider all the cases, okay? So for every 2 vertices, there's a path connecting these 2 vertices, okay? So this is the standard definition. So this is connected, and this is not connected. Sometimes we will call this a disconnected graph. Okay. So we'll take a break after I finish the definition here. Okay. Okay, so here we want to define this word connected. I'll first write down the definition according to his, okay? Okay, so this symbol means belongs to, okay, or in, okay? So this capital V is the vertex set, and this lowercase v is a vertex, which such that or I'll use the term path, okay? But if you're not sure about this path, I'm going to define it later, okay? Okay, so this is so his suggestion. Okay. All right, so let's take a break, and when we come back, we will write down the second definition. That is the standard definition, and I want you to see whether these two definitions are equivalent. Okay, we want to make sure that we have a consistent way of seeing a kinetic graph. Okay, so let's take a break. Okay. Okay. All right, okay, so this is our first version, okay, of the definition for kinetic graph. Now let's consider like the standard definition. Okay. Okay. So this is the definition I think you'll probably find if you Google it, okay? So the definition says it's connected if for every two vertices, okay, for every two vertices in a graph, there's a path between these two vertices, okay? So now it seems like we have two different definitions. So my question is, are they like the same or equivalent? So this means, say I have a graph that satisfies this definition, okay? Is it always true that the graph would also satisfy this condition, okay? And the other way around, say I have a graph that satisfies this definition, will it satisfy this definition, okay? So if I call this definition 1 and this is definition 2, in other words, does definition 1 imply definition 2? And does definition 2 imply definition 1? Okay? Okay. So what do you think? Are these two definitions like actually means the same thing? 所以刚刚第一个 definition 它有点像是它只看一个 vertex， 然后他说这个 vertex 可以连到所有人。然后第二个 definition 看起来比较 strong 一点 ，OK？ 它是说你要确定任两个vertex 它都可以有 path 相连，所以感觉这个比较严格一点，然后第一个 definition 比较宽松一点，所以这两个看似一个比较严，一个比较宽松的，它们事实上是不是一样的定义？所以我刚刚就问说，如果假设你今天有一个graph， 它满足 definition 1， 你看到这个一跟2，你就可以把它想，一就是那个只有一个 vertex， 然后这个一个 vertex 可以连到所有的其他的 vertex， 然后 definition 2就是那个你要考虑所有两个 vertex， 然后确保它们之间有 path 相连。所以一能不能 imply 2？这应该没有太困难。所以如果你有满足，你可以找到一个 vertex， 然后这个 vertex 可以连到所有人，那你能不能确保任两个中间一定会有 path？ Any idea? Okay, so so if the graph satisfies the first definition, this means there's a spatial vertex V. This V is like a hop, okay, because it can be connected to any other vertices in the graph, okay. Okay, so now can you use this spatial vertex V to argue that for any two vertices, I can always find a path? Say we call this any two vertices A and B, okay? Okay, so the goal, or your goal, is to show that there must be a path between A and B in the graph. So how to do this?
There's the path from A to B and another path from B to B.
Yes, so OK， 所以我们刚刚已经有说 V 它是一个类似一个 hop， 所以A 跟 V 会有 path， 同样的 V 跟 B 也会有 path， 所以我们就可以把这两个 path 组合在一起，然后它们就可以是一个连到 A 跟 B 介于 A 跟 B 中间的 path。OK， 视觉上有点像这样子。那我基本上就是我这边下面画的 ，OK， 所以这就是一个连接 A 跟 B 的 path。But there's a small problem here, okay? So now we have two paths, okay? It's kind of we just need to concatenate these two paths. But when we concatenate these two paths, what is the result? Is it still a path? You have one path and another path. Will the result still be a path? So for example, you have A and this is V. Okay? So this is the path between A and B. And say you have a path like this. And this is B. So you have two paths, okay? This one path, the green one is the path between A and B, and the yellow one is the one between V and B, okay? And we just say you concatenate these two paths, is this a path? 这 path 的定义是什么？换句话说，我们确实可以从这个 A， 然后根据这个，然后走到 B， 但是我们可以说这样的走法是一个 path 吗？ OK， 有人说可以，有人说不行。严格的定义是这个不是一个 path。OK，so it seems like I have to first define what a path is. Okay. So we use this word a lot. Okay, but what really is a path? 什么是一个 path？所以先讲结论，这个不是 path，OK？、所以你的定义一定要 somehow exclude this as a path，OK？、So for example, let me give you a wrong definition for a path, okay? So if you define a path as like a sequence of edges and vertices such that you can go from some vertex A to some vertex B, okay? If you only consider this a sequence, okay, so that it can bring you from the starting point to the end point, then this is definitely not a correct definition because this definition will say, well, this one is also a path, okay? But I want to exclude this as a path, okay? So the key difference is that whenever I visit like this vertex here, when I first use this green path to reach the third vertex, then in the future, I cannot visit this vertex again, okay? Because then I'll visit this twice, which means there's like a cycle or a loop on the way to reach the final destination. So we do not allow loops in path. We do not allow cycles in path, okay? So every vertex can only be visited at most once, okay? You cannot visit twice or more. So this is not a path. Okay, so for a sequence of vertices to be a path, it has to satisfy two properties. So the first one is the most natural one, that is, if I say I can use this path to reach from V1 to Vk, then you have to make sure that V1 and V2, they are adjacent. Okay, there's an edge between V1 and V2. Similarly, there's an edge between V2 and V3. Okay, so that's very natural. So Vi and Vi plus 1 are adjacent. Okay. Or okay. because you cannot use edges that that are not on the graph. And okay, so this is the way to say we do not allow repeated vertices in the sequence, or we can at most visit every vertex at most once. Okay, so in other words, V1 and V3 they cannot be the same. Okay, V2 and V4 they cannot be the same. Okay, so once you have this condition, there's no repeated vertices in the sequence, so that's a path. Okay. 好，所以这边就是只有2个关键。第一个关键就是在这个 path 里面你经过的 vertex， 第一个、第二个、第三个、第四个，它们接续出现的这些，它们一定都是相连的。OK， 所以就是在第一个 property 这边。然后第二个 property 就是刚好提到了我们要想办法让上面这种东西是排除在外的，所以上面这种东西它不是 path， 因为它会让我们绕来绕去有 cycle， 会重复经过一些点很多次所以我们要避免这种事情发生。所以我们这边加的 property 就是每一个不同时间点 access 到的 vertex， 它们都是不同的。OK。所以像刚刚这个的话，你可以把它想成这个是OK。So in this case, the length of the sequence is 14, okay? And this is not path because we can see that V3 and V13, they are actually the same vertex, okay? So this violates the second property. And for this vertex, V5 and V10, once again, they're actually the same. So yeah, this does not satisfy the second property that I just wrote down. Okay, so this is not a path. Okay, so this brings us to the second question. So if I cannot just simply concatenate these two paths, how do I get the desired path between A and B? So 我们刚刚的目标是 OK， 我有一个 hub V， V 可以连到所有人，但是我们现在想要说明说，这个 definition 只看一个点的 definition， 跟看任2个点的 definition， 我们要说明说它是一样。所以我们刚刚才会有这个 idea， 就是 A 先走到 V，V 再走到 B。OK， 那我们希望说，如果很直觉，这个 AV 绿色这一段跟 VB 黄色这一段，它们是没有任何的交集。那你就直接把它串起来就可以，串起来就是一个 path，OK？ 那如果串起来中间发现有交集的地方，那怎么办？你要怎么在这个图上面找到一个 path？ 不过这有点像程式竞赛，如果是程式竞赛，可能大家会觉得很简单，就是你的 input 就是2个 path，OK， 绿色这一条跟黄色这一条，然后我可以保证说这个2个 path 它们有一个共同的 endpoint V， 你的目标是要去 output 一个 path 从 A 到 B， 要怎么做？Find what?
Find the same vertex.
The same vertex?
Between two paths.
What do you mean by the same vertex between? Oh, you mean this repeated duplicated vertex? Okay, and then?
And then we can start from A.
Uh-huh.
We keep going when we meet the first same vertex.
Uh-huh, uh-huh, uh-huh.
Let's say the vertex is X. So we have the path from A. We have a path between A and X.
Uh-huh.
And there's another path between X and B.
Right. Let's, yeah.
Yeah, so A, X, and B is the path.
Okay, so let's write out this algorithm, okay? By the way, there can be many different ways of doing this. For example, you can, save this graph, save this concatenation between these two paths as a graph, and use any like shortest path algorithm to find the shortest path between A and B. That's one way to do this, okay? But what Melvin just suggests is, I think his suggestion is better than mine, okay? I'll just write a path in, we have a green one and a yellow one, okay? Oops. Okay, and let's call this X. So I think I have to add this first because there can be multiple duplicate vertices on the green path. And I think it's critical to choose the first one. Otherwise, I think there will be some problem. Okay, so we really need to like traverse from the start of the green path and step by step check whether this one also appears in the yellow path. If so, then this is the first duplicate vertex. By duplicated, I mean it also appears in a yellow path. OK，所以就刚刚第一步就是从这个绿色的这边走到第一个跟黄色有交错的。所以如果在这个示意图的话，这个就会是 ，oops， ，OK，X。And basically, you can go from, recall that this is A, and this is B. So A, X, B is a path. So how to convince yourself that this concatenation, again, this is like a join two path, okay? But the problem we have previously is that we cannot just naively join these two paths because we may have some duplicate vertices, okay? And so the only modification we do here is that we will switch from the green one to the yellow one once. It's like once we encounter the yellow one, we will switch to the yellow one, okay? Is it a path? So why? So you have to show that for this one, really there's no duplicated vertices. 这样走真的不会又再交错，又再回到我们之前经过的点。所以有没有可能这样走，它还是经过之前某一个点？ Okay, so this brings us to the first, I'll say the most important proof technique, that is proof by contradiction, 反证法. Okay, so when proof by contradiction is applied to this statement, this means, so let's think, okay, so what happens if this is not a path? And try to find some contradiction. And if you can find some contradiction, then you're done. Okay, that's the idea of proof by contradiction. So let's assume that this is not a path, meaning when first of all, this must be a path, right? Because this is the green one, a subpath, okay? So if only take a portion of a path, it must still be a path, right? So this is a path, this is a path. So if I say that this is the whole, the join of these two paths is not a path, then it must be the case that when I traverse along this yellow path, it somehow go back to the yellow, or visit some vertex on the green path. But is it possible? Visually, this looks like this, okay? So I first traverse along the green one. Okay, so this is A and this is X. So this is X. Therefore, I then detour and follow the yellow one. Okay. But I said that let's assume that this is not a path. So this must be the case that I then visit some vertex on the green one. To reach B. Okay. This is the only reason that this is not a path. Okay. But then, can you see the contradiction? So what's the contradiction? 所以矛盾的点在哪里？ Exactly. So that's why we have to use this modification. So we have to make sure that the duplicate vertex is the first one. Okay? And it also improves like the efficiency of the whole algorithm, because all you have to do is to traverse along the green one step by step and check whether it also appears on the yellow one. Okay? So you can like store all the vertices for the green one and the yellow one on a hash table, so it takes that constant time to check whether this vertex also appears on the yellow path, okay? Right, so this algorithm is definitely better than mine. where my algorithm was just use some Dijkstra algorithm or shortest path algorithm or BFS to find a path on this kind of graph. Okay, so yeah, yours is better. Okay, good. Okay, 有问题吗？我要说一下，就是刚刚那个的都是有点像是 ad hoc，就是临时产生出来的讨论。那我自己蛮喜欢这样的讨论，就是如果同学，大家回想一下，刚刚会有这些讨论，是因为我问大家说 connectivity 的 graph 一个 connected graph 它的定义是什么？那其实我坦白讲，我本来没有想到这个定义 ，OK，我本来准备要讲的是这个定义 ，OK，那我觉得因为这门课修课的人没有很多，所以我觉得修课少有修课的好处，就是我们可以量身定做 ，OK。那同学有一些回应是跟我想象的不一样，我觉得非常好，我们就可以花一些时间来讨论这些意料之外的东西 ，OK。所以如果你们有任何想法，可能你的想法跟我的是不一样，你的定义跟我是不一样，你的演算法跟我是不一样，就很欢迎提出来讨论 ，OK。有时候我们可以发现一些新的东西。好，所以到这里有问题吗 ？OK， good. All right, so now we've shown that definition 1 implies definition 2. Now let's consider the other round. Okay, the other way around. Okay, so let's start with definition 2 and see whether we can, arrive definition 1. And this kind of discussion is also very common in graph theory, or actually any branch in mathematics where you have seemingly different condition or definition, but it turns out that they are the same. So yeah, the nice thing about this is that you can have different angles, okay, different viewpoints to see the same concept, okay, and it's usually a nice thing. So definition 2 implies definition 1. Okay, so recall for definition 2, this means this is like a stronger definition. It requires that for every 2 vertices, there's a path. Okay, so very, very strong. Okay, but for definition 1, we only need to find one specific vertex, such that this vertex can be, connected to every other vertex in the graph. Okay, so this is a rather weak one. A stronger one implies a weaker one. This is usually easier, okay, compared to the other direction where we have a weaker definition, and magically we show that this weaker definition actually implies the stronger one. Okay, but for this one, it's quite trivial. All right, so can you see why this is true? 可以看出来为什么？如果任2个你都有 path 相邻，那你一定可以找得到，不是相邻 ，sorry， 任2个点你都可以找到一个 path， 那你就一定可以找到一个很特别，刚刚我说的那个 hop， 然后那个 hop 可以让这个点连到所有 graph 的其他点，这个要怎么说明？ So for definition 1, we have to find this spatial vertex V, right? The hop, okay? The one that can be connected to every other vertex in the graph. So the problem is how to find this hop V. Once you have this hop V, the proof is done, okay? 所以在这个情况下，那个 V 要怎么找到？如果我跟你说任2个点，它们都有 path 相连 ，OK？ 那我要怎么找到 definition 1里面的那个 V？ 有想法吗？有吗？没有，有想法吗？知道我问题吗？有想法吗？OK， 所以每一次因为我刚刚说这个是很 trivial 的，这是很简单的。那如果今天问了一个很简单的问题，然后大家没有想法，那只是代表一件事，就是我没有讲清楚。因为我只要讲清楚，铁定就是你们应该要很容易就可以理解。所以问题不在你们，问题在我身上。OK， 我们现在要证明的事情是，我把这个整句话写出来，然后看，这样你们比较可以理解这句话这个箭头是什么意思。OK， Okay. So this is kind of long, but for the first part, it's kind of setting the assumption. Okay. Okay. So the assumption is that we have a graph, and in this graph, for every two vertices in the graph, okay, there's a path. Okay, that's the assumption. 这是你已知的假设 ，OK， 所以这不是你要证明的，这个是你本来的手上的那个 graph 就已经有的性质 ，OK。So given this graph, okay, you need to show that you can find a vertex v in the graph, okay, the same graph, okay, such that this vertex v it can be connected to every other vertex in the graph, okay? In other words, there's a path between this vertex v and any vertex in the graph, okay? So all you have to do, so if you want to prove this, so this is not proof, this is statement. So this is the statement that we want to prove, okay? Okay, so if you want to prove this statement, you only need to do one thing, okay? The one thing is you have to find a vertex v such that this v can be adjacent, can be connected to every vertex in the graph. OK， 所以我可以用中文再讲一次，就是你手上有一个 graph，OK， 然后这个 graph 你已经知道说任两点都会有一个 path，OK， 大家都知道 path 是什么 ，OK， 任两点都会有一个 path。那我们现在要说明的是，你现在要去证明的事情是在这样子的一个 graph 里面，你一定可以找到一个特别的 vertex v。那这个 v 呢，它有 path 连到所有的这个 graph 的其他的点。 OK， 所以要怎么样找到这个 v？ 怎样的 vertex 有满足这个 v 的条件 ？Every vertex. OK, so because for any two vertices, there's a path. OK, so actually you can pick any vertex in the graph. According to this assumption, this v, well, there must be a path between it and any vertex in the graph. OK. OK， 所以就是这边说的事情是，如果任两个点都有 path， 那你就随便挑一个 path， 随便挑一个 vertex， 那个 vertex 当然也会跟其他的点都会有 path。OK， 所以不知道这样大家有没有比较理解这个方向，我们要去说明。如果你觉得这个不是废话嘛，那某种程度这是废话。OK。所以这个 part 其实是很，我刚刚说是很 trivial 的事情。这个前面这个 part 才会是比较有料的东西。OK。Okay, so now we have shown that definition 1 implies definition 2, and definition 2 implies definition 1. So the result is that these two definitions, they are actually equivalent. They're the same, okay? So you can use whatever definition you like, okay? But as I just mentioned earlier, that usually the standard definition is definition 2, not definition 1, okay? So I guess the reason is that if we consider directed graph, that is, edges have directions, okay? Okay. So naturally, if you want to define a path on a directed graph, and you also have to satisfy the direction. Okay. So when you write down v1, v2, v3, okay, so they are not just adjacent. Okay, v1 and v2, there must be a path that is directed from v1 to v2. Similarly, the next path should be an edge that is directed from v2 to v3. So you have to obey this direction, okay? And so when you have the notion of direction, I think it's somewhat easier to extend this definition to directed graph, because all you have to modify is that there's a path from U to V, okay, for any two vertices, U and V, okay? But here we need to consider UV and VU as different pairs. In other words, we have to consider ordered pair, okay? For any ordered pair of vertices U and V, there's a path from U to V, okay? 所以如果是 direct graph 的话，我们就要考虑方向性 ，OK？ 所以这边就不是说 UV 之间 ，OK？UV 之间就没有方向的概念。那如果我们可以说，是从 U 到 V， 那这就有方向的概念 ，OK？ 那既然有方向的概念，从 U 到 V 跟从 V 到 U 就是不一样，所以我们就要区别开来。所以这边可能就要讲得更清楚一点，这个是我们要考虑顺序 ，OK？ 所以 UV 跟 VU 是不一样，所以你可以这样子去调整，让你可以适用在有方向的 graph 上面。OK， 那这个其实也不是不行啊，但是就会稍微，你可能就要说，V 到所有其他点都有 path， 而且其他点到 V 也有 path， 就是一去一回。OK， 但 anyway， 我们这门课不太会去讨论有方向的 graph，OK， 我们大部分都是讨论没有方向。好，有问题吗？OK， so next I'm going to define another word that I'm going to use a lot throughout the course. That is component. Okay. All right, so this is one graph. So this is not a connected graph, it's disconnected. And my question is, how many components are there in a graph? 有几个 components? I know I haven't defined component, okay? But I think it's a natural question to ask. So how many components? What's a reasonable answer for this question? 3, right? Okay, so one component here, and one component here. So 3 components. Okay. Anyone has a different answer? 大家有觉得3是不合理的吗？就我刚刚说有几个 component，OK， 所以应该大部分都会觉得3是一个蛮合理的答案 ，OK。所以一样，我的问题是 ，then how to define a component? You have to define component so that when you apply your definition to this graph, it says 3. So what's a proper definition for a component? Number of connected graph. Okay, perhaps a small modification, like because we only consider graphs, that is like a portion of this whole graph. So my modification would be subgraph. That's 子图. That is just you can only pick the vertices and edges in the original graph. So that's subgraph. Perhaps I can write out a definition later. But so what you suggest is that the number of component is the number of connected subgraph in a graph, right? OK， 所以大家觉得这个定义有问题吗？就是我如果要去算有几个 component， 我就要去算在这个 graph 里面有多少个子图。子图就是我刚刚说的，你只能选里面的点跟 edge， 然后这个子图要是 connected。所以大家觉得这个数字 apply 到这边的话，会不会是3？如果只是去 count 有多少个 subgraph 它是 connected。So this is like I'm not sure whether you have this kind of questions before. So how many rectangles are there in this picture? Right? So intuitively you may say, okay, 6, but turns out that you can also pick this one. So there are actually more than 6. So similarly, there are many kinetic components, many kinetic subgraphs, right? So you can pick this 4, this is a kinetic subgraph. You can pick this 3, which is also a kinetic subgraph. So the answer would be much higher than 3. So you have to get or add more constraint to your definition. But that's a good start. Obviously, you want to consider only kinetic subgraph. But kinetic subgraph, well, it's still too loose. Okay, you have to add more constraint. Okay. So let's first take a break and see whether you can find a better definition for a component. Okay. Ah, 我再帮你讲，对，我再帮你讲。
识一下大家，因为有一些是我学生，我知道，所以是大学部还是硕士班？硕班。那你是哪个老师？邱老师。邱淑雅。对，邱淑雅。哦，OK。啊，所以后面同学是大学部。大三啊。交换学生啊。但是是大学部的交换学生还是硕士班？大学。哦，OK。啊，就是邱轩。
All right, so back to the definition of component. So the first attempt by Yixiu, right? Yixiu, okay. So his suggestion is a component is a connected subgraph. Okay, so that's our first version. This is not correct, but this is a good start. Okay, so this is not correct because if you apply this definition, then you have more than 3 components. Okay, so we need to add more constraint. So previously I said if we apply Yixiu's suggestion, then we will have this as a component. We also have this as a component. We can also have this as a component. Okay, but intuitively these 3 should not be considered as a component. So why? I'm sure that when I first asked this question that how many components are there, the reason that you said 3 is because you think this is a component, and this is also a component, and this is a component. That's why you say 3, okay? So the reason or the problem with this being a component is that this is too small, right? And similarly, this is too small, okay? The green one is a component, not the other one, okay? So again, this is too small. So how to modify the definition so that we can actually increase the size of component, or make sure that we cannot consider these smaller subgraphs as a component. I want to add more description to the definition. 我们要加一些限制，加一些描述。在刚刚Yixiu的建议就是任何一个 connected subgraph 都是 component。OK， 但有点太宽松了，我们需要再加一些限制。要怎么加这个限制？A biggest, this makes sense, but what do you mean by independent? That vertex again? Oh, 你的意思是说，我如果绿色这边选起来，我这边再选的时候，不能再选到这边，是这个意思吗？Oh, okay, but that's not a problem because if you already choose this as a connected subgraph, then you cannot add this vertex because then it will be disconnected, right? Because there's no edge between this vertex and this component, okay? But just as you say earlier, you have to make sure that this is connected, okay? So once you said that this is connected, you exclude the possibility that you have this and this as one component. So this is impossible, okay? And yeah, so, but the other phrase that you add is biggest, all right? So we want to find the biggest connected subgraph, okay? Now, so if you only consider biggest connected subgraph as a component, then how many components do you have? If you only care about the biggest. By biggest, I mean we count the number of vertices, right? Okay, because you haven't said how do you measure like the size, okay? But I assume that you mean the vertices, okay? The number of vertices. So if you only choose the biggest or the connected subgraph that contains the most vertices, then you can only have one, this one, because this one has 5 vertices, this one 4, this 3, so the biggest one is this one. So according to this definition, Well, we can only look at this component. So the answer would be 1. There's only one component in a graph. So compared to your first version, this version is like too restricted. Okay? You add too many constraints. This biggest is like too strong. Okay? We need to find something like in the middle. Right? Not necessarily the biggest. 那就是刚刚一修说的是，我们就找到那最大那个，因为刚刚的问题是这个黄色这些都是太小了 ，OK？ 但是如果我们真的要 biggest 最大的那个，那就是看起来就只有选这个而已 ，OK？ 我们需要其他的方法，所以换句话说，刚刚一修有点像矫枉过正的感觉，一开始是黄色太小 ，OK？ 所以会让你选一大堆的 subgraph 变成是 component， 但现在如果我只看 biggest。又会变成我只能选一个，有没有什么介在其中的方法？
And if you add any other vertex to this subgraph, it won't able to be connected.
Very, very, very close. The only small problem is that when you say 8 vertex, because if you only add vertex, like consider this triangle, okay? Let's add this vertex. Is it connected or not? If we only add this vertex, not these edges, right? So, but I get your point, okay? So, Melvin says, 他的意思就是，什么是一个 component？ 就是你再加任何一个其他的 vertex，OK， 可能然后再加上一些其他的 edges 之类的，你都没有办法让它变成是 connected。所以换句话说，像这一个，它就是一个 component， 因为你没有办法让它变得更大。简单来讲就是这样子 ，OK。所以像这个你没有办法让它变大更大，因为譬如说你想要让这个也加进去就不可能。因为这样就不会是 connected，OK？ 所以记得刚刚一修提到一个关键就是要是 connected。那现在Melvin 的建议是我们要确保说它不能再变得更大，你找不到一个更大的去包含它 ，OK？ 所以像这个，你事实上就可以找到一个更大的，然后可以包含它，就是这个更大包含它，而且是 connected，OK？ So a component is a connected subgraph. Okay. So subgraph is just like only a portion of the graph. Okay, so let's subgraph. Such that no larger subgraph, connected subgraph contains it. Okay. So let's try to apply this definition to the graph. Okay, see whether. So is this a component according to this definition? So if this is a component, then it has to satisfy this property. Okay, this is this constraint. But for this triangle, we indeed can find a larger, connected. Okay, so we can find a larger connected subgraph that contains this triangle. So this one is not a component. Okay, but for this one, this is a component because there's no larger connected subgraph that contains this one, okay? So this is a component, okay? But if you Google it, you Google the definition of a component, you won't see this, okay? What you'll find is like a shorthand for this kind of complicated definition. So what you'll find is a component is a maximal connected subgraph. Okay, so here the keyword is maximal. And whenever you see words that ends with AL, this means like local, okay? So this means local maximum. So what issue says is, I want to find the biggest. So this is like the global biggest, the global maximum. So if you apply global maximum, you can only find one. But if you only restrict to local maximum, in other words, maximal, then you can find many, many different components, okay? So a shorthand for this definition is that this component should be a maximal connected subgraph. So in short, if we just replace issue association, replace biggest with maximal, then you'll get the definition you're going to find when you Google it. All right, so let's component, okay? Okay, I have to define one more boring property before we can start discussing some interesting problem, okay? So the final boring, not property, okay? So this is, once again, a definition, okay? Degree, okay? Okay, so we can count the number of neighbors for every vertex, okay? So for this guy, we can count the number of neighbors. So this one is adjacent to this, and this. So there are 5 neighbors for this vertex in the middle. So we can write, say this is V. So usually I'll just write D of V or dV, okay? So this is degree of V. Okay? So this is simply the number of these neighbors. Okay? So in this case, dV is 5. And say this is U. So for U, the degree will be 3, okay? Because U has 3 neighbors. Okay? Kind of boring but simple, okay? Just count the number of vertices, the number of neighbors. Okay, so the first, I'll say, interesting question that we're going to consider is the following, okay? So here we're going to consider the relationship between being a kinetic graph and the smallest degree in the graph, okay? So for example, if you consider this graph and say I remove, I add this one, okay? So for this graph, the smallest degree, okay? By smallest, I mean you compare all the vertices and compare their degrees and find the smallest one, find the minimum, okay? So I think it's easy to tell that the smallest degree for the graph is 2, okay? This one, this guy, has degree 2, which is the smallest among all the vertices in the graph. Okay? So the minimum degree is 2. Okay? All right, so we are all set. Okay? Now we can discuss the question. Okay? Okay, so the first one, this is a warm-up question, okay? And sorry, another standard notation that I have to introduce. So throughout this course, we're going to use lowercase n to represent the number of vertices in the graph, okay? So, for example, in this graph, n is 7, okay? Because there are 7 vertices in the graph, okay? All right. Okay. So the question is this statement true or false? So if I give you a graph and I tell you that the smallest degree is m minus 1. So here n again is the number of vertices in the graph, okay? Then is it true that the graph must be connected? 如果这个 graph 我手上我给你这个 graph， 我确保说它的 minimum degree 是 n 减1。In other words, so this means every vertex has at least m minus 1 neighbors. Okay? So if every vertex has m minus 1 neighbors, or in a social network, if every user account has m minus 1 friends in a social network, then the social network must be connected. Is it true? So what will the graph look like? Say n is 10. Oh, no, n probably 10 is too large, so 5, okay, just 5, okay? Sorry. Huh? Okay, so one nice thing about graph theory is that you can always draw some examples, okay? So let's try, n is 5, okay? So 5 vertices, all right? And you have to make sure that in your graph, every vertex has, so n minus 1 will be 4 in this case, okay? So for this guy, the top one, it has to have 4 neighbors. So it has no choice, really, okay? So you have to connect this one to every other vertex. Similarly, for every other vertex, they all have 4 neighbors. So they have no choice. They are friends for every two of them, okay? So this must be the graph that satisfies this condition. Is it connected? Yeah, obviously, because being a connected graph means there's a path between any 2 vertices, okay? So can we find a path between any 2 vertices? Absolutely, because we cannot just find a path, we can find an edge, okay? There's always an edge between any 2 vertices. So certainly this is a connected graph. And actually there's a special name for this kind of graph, that is complete graph, okay? So this is complete graph. And we write Kn, okay? So this means a complete graph that has n verses, okay? By complete, this means for every 2 verses, there's an edge. This is a complete graph, okay? So the answer is yes, okay? So if the minimum degree is n minus 1, then the graph is complete graph. So yes, connected, okay? So this is just a warm up, okay? So very, very easy. So the second one. So the question is very similar to this one, but I'll change this minimum degree. So n minus 1 is like the highest possible degree you can have in a graph. You cannot have degree n, because in a graph of n verses, you can have at most n minus 1 neighbors. So degree is at most n minus 1, okay? So this, for the second question, we were going to replace n minus 1 with n over 2. So it's like if you consider social networks, then every user is a friend of like half of the nodes, half of the users in the social networks. Is this social network connected? OK， 所以跟刚刚前面不一样的是，这个 degree 基本上是砍半，你的朋友数是砍半。刚刚这个基本上是不可能出现在 social network， 如果这出现在 social network 就代表，这应该是会是一个很小的 social network， 所以才保证说两都互相认识 ，OK， 可能是一个 lab，OK， 小的实验室这样子。但这边呢，我们稍微把条件放宽松一点，就是不是每一个人都互相认识。但是呢，我可以保证每一个人都认识至少一半以上的网络里面的人 ，OK？ 然后我想问的是，这样子这个 graph 会不会是 connected？ Again, I want to stress that for this course, you can always try some examples. So what you can do now is that let's make it a whole integer. So let's try n is 6, okay? So please draw some graphs, okay, which contains 6 vertices. If you need papers, you can find it here, okay. So 6个 vertex, okay， 你的图上面有6个 vertex， 然后每一个点它至少要有3个邻居，然后试试看看你可不可以画出一个不是 connected 的 graph。OK， 如果需要的话，这边有白纸，对，我强烈建议大家试试看 ，OK。如果你们没有一些感觉的话，试试看，就画6个点，然后每一个点至少3个邻居，然后看一下你有没有可能画出一个图，它不是 connected。sorry， 几个连着？我说的至少是说每一个点它至少要有3个邻居。对，就是 n over 2， 因为6除以2就是3，对，所以每一个点至少它要有3个 edge 连出去，然后看你可不可以画出一个不是 connected 的 graph。In other words, I want you to find some counter example 反例 ，OK？ 所以看能不能找到反例这样子。 And while you are trying to find a counterexample, you can also think, well, obviously this is true, so I write it down, so this is true, and you'll never find a counterexample. But still, you have to convince yourself. So try some examples. But also you can think, why is this always true? Okay? Can you have a proof for this? So don't just believe me, try some examples. Okay?有人想要分享一些想法吗？比如说，当你发现怎么画都画不出来。第一个，如果你画得出来，那铁定是哪里搞错，就是比如说你的条件弄错之类的。OK， 所以如果真的画出来，也可以举手，就是我可以告诉你，刚边可能哪里有误会，或我讲的不是很清楚。OK， 那如果大家都没有办法画出 counterexample， 那看有没有人可以分享一下，为什么绝对不可能画得出 counterexample？
就是我的想法是，因为它如果要是不是 kinetic 的话，就是变成说我们会要有2个 component。
Right.
那所以我就是用分组的方式，就是1个 vertex 跟5个 vertex， 然后2个 vertex 跟4个 vertex， 3个 vertex 跟3个 vertex， 然后照理来说应该3个 vertex 跟3个 vertex 这样分组应该会有，就是 minimum degree 会是最大的情况。在这个情况下，也只会有2，不会有3。
Right. So actually, we can transform this idea into a formal proof. Okay. So what you should suggest is that like a proof by contradiction. So let's assume that this is not a kinetic graph. So you have at least 2 components. Okay. Then the key observation is that if you have 2 components, and what is the minimum degree? And then try to find some contradiction. Okay, so let's write it down. Okay. Okay, so 反证法 contradiction. So we assume the graph is not connected. Okay, therefore it has at least 2 components. Okay, so if a graph is connected, then it has exactly 1 component. Okay, and whenever you have 2 or more components, well, this is not connected. So the graph we have has 2 components. At least, okay. So we want to find some contradiction. So where's the contradiction? 矛盾在哪里？怪怪的点在哪里？如果它真的有2个 component 的话，会违反什么性质？ So Isho just mentioned that, say, this component has 2 vertices and this one has 4 vertices. Then what is the minimum degree for this kind of graph? 1, right? Because let's consider the vertices in this component, this smaller component. The degree is at most the number of vertices in the component minus 1, right? Because you cannot be a friend of yourself, okay? There's no self loop, okay? So, yeah, so for this one, the minimum degree is at most 1. So this is a contradiction because here we said that the minimum degree is very high, okay? So it's at least n over 2. This is a large number. But for this one, turns out that the minimum degree is very small, right? So that's a contradiction. So that's the key idea. But somehow this is not a formal proof because we cannot say that there must be a component of size 2 and a component of size 4. No, we cannot do this. So we have to somehow make this idea more formal, okay? So let's consider, the key idea is to consider the smallest component, just like what we did, okay? So if you have a component of size 2, another of size 4, then let's consider the smaller one, okay? So since we have multiple components, we just consider the smallest component, okay? Now what can you say about the size of the smallest component? So we want to make sure that this smallest component is very small so that the minimum degree is too small compared to this number, okay? So we want to find some upper bound, okay? So this is 至多是多少, at most, okay? So in the previous example, we can say that the minimum degree is 至多是1, okay? Or if the component has sizes 3 and 3, okay, 3, 3, then the minimum degree is at most 3减1就是2, okay? 然后就可以跟这边有一些矛盾, okay? So what is the number here, okay? So this number is at most like half of the vertices when you split the vertex set into 2 balanced sets, okay? So n over 2 for one set, and another component also has n over 2 vertices, okay? So this is like we have 3 and 3, okay? For the case of n being 6. So we have a component of size 3, another component of size 3, okay? So we know that this yields a contradiction because this minimum degree is at most 2, okay? So the minimum degree is very small, okay, compared to this one, okay? OK， 所以有问题吗？所以我们这边主要就是根据易修刚刚的建议，就是我们有多个 component 的时候，我们去看那个比较小的 component。那个比较小的 component， 它的里面的 degree 就不会太大，因为那个 component 的点，它的邻居就也在那个 component 里面，所以就让那个小 component 的里面的 vertex 都一样会有很小的 degree， 然后就可以拿到矛盾 ，OK。所以我们这边做的是只是唯一的差别，刚刚易修的建议就是我们明确写出来说，最小的 component 它最多就是 n 除以2这么多个点。那如果你最多只有 n 除以2个点，那 你的 degree 事实上最多只能到 n 除以2再减1，不会到 n 除以2。OK， 所以就是有差1啦。OK。Okay. Any questions?
So we just talked about the definition of connected
Okay.
Directed graph.
Mm-hmm.
So I'm wondering if there's a connected definition for directed graph.
Connected graph for directed graph. Yeah, so there are actually two types of connectivity or connected graph for directed graph. The first one is strong connectivity or strongly connected, sorry. Okay, and the other one is weak connected or weakly connected. Yeah, so I believe so. So two types of connected graph. Okay, so the first one is strongly connected. And the second one is weakly connected. Okay, so the difference is that when you consider a path for a directed graph, you have to consider direction. So the major difference between these two is that for strongly connected graph, for any two vertices u and v, you have to make sure that there's one path from u to v, okay? And also a path from v to u. And this is true for every two vertices, okay? But for weakly connected graph, I think if my memory is correct, you only have to make sure that either u can find a path to v or v can find a path to u, okay? Just one of them. So for this, we require both direction. And for this, we only need one of them. Yep. But I think you have to double check it. Okay? Yeah. But I'm like 99% sure that I'm right. 如果你的图是有方向性的话，基本上我们就要考虑 edge 的方向性。所谓 strongly connected， 如果我的印象是对的，就是它要确保说任两点，它都可以从 u 任两点 uv 我都可以找一个 path 从 u 走到 v， 也可以从v 走到 u， 两个方向都要可以，这样就是 strongly connected。OK， 那 weakly connected 我的印象是就是你只要其中一个就可以。OK。Okay, are there any questions? Okay, so back to this question, okay? So for this question, we just give you a proof based on contradiction. So usually the proof, if you prove something by contradiction, the proof cannot reveal too much detail or information or structure about the graph, okay? Because after you see the graph, after you see this proof, you cannot infer any further information about the graph. So next I'm going to give you a different graph, a different proof that can reveal more information about the graph. So remember when we discussed the first question, it turns out that for every two vertices, there's an edge between them, okay? So this is when the minimum degree is super high, like n minus 1. Then you get an edge between any two vertices in a graph. Now, when the minimum degree is n over 2, this is still very, very high, okay? So this is a very dense graph, okay? So it turns out that even though we cannot ensure that there's always an edge between any two vertices, like a complete graph, but actually we can show that if there's no edge between u and v, okay? No direct edge, okay? In this case, you can always find like a common friend, a common neighbor of these two vertices, okay? So in short, for this kind of graph, it is not just connected. We can always find a common friend for any two vertices in a graph, okay? So let me write this down, okay? So this is W. W is a common neighbor of U and V. Okay. Okay. I think I don't have time for the proof, but I can explain this statement, okay? So if the minimum degree is n over 2, okay? Turns out that if you have two vertices and they are not adjacent, meaning there's no edge between them, like U and V in this case, you can see that there's no edge between U and V, but we can still find a very special vertex, a common neighbor, okay, between U and V. Okay. So if this is true, then obviously this is a kinetic graph because for any two vertices, either they are adjacent or they have a common neighbor. Okay? So this must be a kinetic graph. Okay. Or a different way of seeing this is that for this graph, what is the shortest path distance between any two vertices? What is the shortest distance? 最短的距离是多少？对任两点来讲，它们最短距离。这边最短距离是定义在它需要几个 edge 才可以走到对方。So for this graph, the shortest distance between any two vertices is 1. Okay? Okay? So this is for complete graph, but for this case, if for any two vertices, if they are not adjacent, then there's a common neighbor, then what is the shortest distance? The shortest distance is at most 2. Okay? Okay, so you can think about this like this. Okay, so if we just know that a graph is connected, and then the shortest distance can actually be quite long, okay? But once I tell you that the minimum degree is sufficiently high, like m minus 1, then the distance becomes 1. And if the minimum degree is n over 2, then the shortest distance becomes 2. Okay? So when I lower this minimum degree, like I can, the shortest distance is increased. Okay? So there's a relationship between minimum degree and the distance. Okay? 所以这边要刚刚讲的就是，如果你去调整你的 minimum degree 的话，就这个整张图里面，每一个人至少多少个邻居 ？OK？ 如果这个最小的邻居数是很大，像 n 减1的话，那基本上最短的距离对任两点来讲都是1。那如果你把它从 n 减1缩小到 n 除以2的话，那这个最短距离就会变成2。OK？ 不过我们今天没有时间去 proof，OK， 所以这个 proof 会留在下礼拜。那如果你有兴趣，我没有做过，但你可以去问 Gemini， 问 ChatGPT。如果今天我想要让这个2变成比如说3好，那有没有办法找到对应的 minimum degree， 或者是对应的 condition， 让它保证说，任两点的距离至多是3。同样的，至多是4有没有可能？至多是5有没有可能 ？OK， 所以大家回去如果有兴趣的话，可以用 Gemini 或 ChatGPT 试一下。OK， So that's all for today. All right, so see you next week.